So we've got a bunch of course stuff sorted out. For example, the logic labs will begin this week. So these are the locations for this week. They'll almost always be in the same room. The Thursday instance is an exception. It's in a slightly different room than it'll usually be. But this is posted on Quarkus. It'll be the same time every week, Thursdays and Fridays. And we did it that way because I'm going to post an exercise at the beginning of the week. I'll teach you how to do that exercise on Monday and Wednesday. Then you've got Thursday, Friday to get help from the logic lab. And then on Saturday, the exercise is due. So that'll be our weekly schedule, basically the whole rest of the semester, with one or two minor exceptions, but that's the plan. So to reiterate, the logic lab is not a standard tutorial. You're not required to attend. There's no lesson plan at the logic lab. So if you show up to the logic lab, they're not going to be, hello everybody, welcome to logic lab, here's what I'm going to teach you this week. It's just a space for you to come and get help on your weekly exercises or anything else in the course that you're confused on. There'll be one or two TAs at the logic lab who are undergraduate students who have taken this course and done really, really well in it. They're fantastic people. They were running the logic lab last semester with me, so we're sort of got a well-oiled machine now. So strongly recommend that you attend these. Get some help on the logic lab or on the exercises. You do not have to do those exercises alone. So this is unlike practically everything else in your university career. This is not supposed to be just your independent work that you're getting credit for. You can get help and then submit the exercises and get credit for it. So check the assignments section. There's now an assignment section on Quarkus. Check the assignments section to see which questions you need to answer. And then you'll answer them in Logic 2010, the program, submit them in the program, and then it will show up on Logic 2010, the website, that you've submitted them. So there's three parts to this. There's the Quarkus, there's the program, and then there's the website. And I want to walk you through that now because this is slightly more confusing than one might find optimal. So let me just show you that right now. So Quarkus, I'm sure you can find on Quarkus what the exercises will be. Here they are. So here's a list of the questions that you need to answer for this week's assignments. So let me show you how to find these questions, how to answer them, and then how to submit them. So you're going to download onto your computer Logic 2010. The link is on Quarkus for where to find the program. You're going to download it. You're going to register for this instance of the course. So there are instructions on Quarkus on how to do that. And then you're going to click on one of these modules. So these modules are where you find the questions. So for this week, the questions are symbolizations 1, 2, 3, 4, 8, and 9, and derivation 1, 2, 3, 4. So I'll show you today how to do the symbolization questions, and on Wednesday, how to do the derivation questions. So let's start with symbolization. So you're going to go into these. Beautiful Logic 2010. And then you're going to select, it's free, okay? It's free. All right, you're going to select the question. All right, so these are the questions you're going to select from. I'm going to say, okay, I'm going to select 001. So I'll delete my answer on this. And then you'll complete the question. Just quickly, so on a PC, you right-click. On a Mac, you control-click. And then I'll explain how to actually answer these things in a bit, but I'll answer the question. I'll explain this once we get to symbolization. And then once I've answered it, I say check. In the top right-hand, it'll say correct. And you'll think, hooray, I've done it. I've completed my task. But you have not yet completed your task, okay? There's a couple more steps. You need to click submit and enter your password. The password you enter is one of your own construction. It should be something that's easy to type because you're going to have to type it a lot. So, okay, and then it's going to ask you to confirm that this is the course that you're enrolled in. If it looks like this, then you're on the right track, right? U of T, Spring 2019, Philosophy, PHL245. Instructor, Corey Travers Lewis, that's me. So you say okay. And then you select which question you want to submit. You can submit multiple questions. So if I'm holding Shift, you could submit multiple questions, but suppose I just want to submit this one. So I say submit, and then all problems were successfully submitted for Corey Travers Lewis. Hooray. Okay. Now, that was submitting the question. So you're going to go through each of the questions in the exercises and submit them. Now, let me show you how you confirm that your exercise was successfully submitted. This is important because a great number of people will come to me and say, I finished the question, but for some reason it didn't submit. I'm going to show you right now how to make sure that it's submitted. Okay? So that's on the Logic 2010 website. So here's the Logic 2010 website. Again, the link is on the Quarkus. And on the Logic 2010 website, you can see here's the list of assignments. So the Lewis number 1, this is our weekly exercises, number 1. And here's the list of problems that we've got to solve. And you can see in this column under score and eval, you can see C is for complete. Complete means that it was successfully completed and submitted. You can see for the rest of the problems, I have not yet completed and submitted them. Okay? So this is very, very similar to what I'm going to see when I'm checking whether you've done your assignments or not. And it shows me the date at which you submitted it. So if it's submitted after the due date, this will say late, and you won't get the marks. Okay? So quickly, one more. I'm going to select another question. Ina will not fail to be chosen as campaign manager. So again, I'll show you this shortly. So negation, atomic P. Right? I'm going to check that my answer is correct. Hooray, it's correct. And now, okay, so currently I have nothing submitted for symbolizing question 2. But once I go to submit, enter my password, say OK. I'll click on this one on 002. I say submit. I say all problems successfully submitted for Corey Travers Lewis. And it tells you which problems were submitted. Now I can go to the website and check. Look, now question 2 has been successfully submitted. Okay, so you get immediate feedback on whether it was successfully went into the system. I check on the Logic 2010. So Logic 2010 tells me whether you completed the task. So you can see what I see when I'm checking to see whether you've completed these exercises or not. Okay? So there's a list of questions on Quarkus. You can also look at the list of questions on the Logic 2010 website. You complete those exercises in the Logic 2010 program, submit them, and then you can check on the website whether they were successfully submitted or not. Okay? Is that reasonably clear what the process is? Nobody's immediately objecting. You can, if any of this is unclear, another thing that would be good to ask at the Logic Lab is, how do I deal with Logic 2010? So there's going to be, probably you're going to have questions because it is not the clearest program in the world to work with. Just want to point out one other thing on the Logic 2010 website. So this was under the assignments tab. So you got the select course tabs where you can choose which course you're in. If this is your first time in Logic, it'll just be one course. There's the assignments tab, which is what I just showed you. There's also the documents tab. And under program documents, there's a whole bunch of useful documents. So like here's the Terry text, here's the textbook for the course. Here's a bunch of stuff about, for example, installing Logic 2010, using Logic 2010, saving, submitting, backing up, how to use all of the manuals, all of the modules. So there's a whole bunch of FAQs and instructions on the website that you can access. So if you're having trouble, this would be a good place to start. If you're still having trouble, the Logic Lab is another good place to ask for help. Okay? So I'm going to go through, as we get into each of these modules, I'm going to go through the controls and exactly what you do to solve these things in more detail. So we'll start with symbolization today. We'll do derivations on Wednesday. Good so far? Good. Okay, so here are the exercises for this week. There may be fewer questions in some of the exercises, but they're all worth the same. Worth nothing, by the way. There are 10 weekly exercises. That's 15% of your final mark. You get 1.5% of your final mark just for doing this. And at the beginning, this will be really straightforward. They'll get harder as we go along, but that 15% is kind of a gift because you can try these as many times as you want. I got it right the first time, but like if I'd failed to get it right the first 15 times and I got it on the 16th time, I would have got full marks for that. So get those 15%, don't miss out on them. If you can't figure it out, go to Logic Lab and ask for help. If you can't make it to Logic Lab, go on the discussion board on Quarkus and ask for help. So get those marks. Don't leave those lying on the table when you have the opportunity to get a pretty straightforward 15%. Okay? Okay. So let's get into logic then. If there's not any other course business questions, we'll get into some logic. Okay, we're starting in on sentential logic, the logic of sentences. The basic element of sentential logic is a proposition. We talked a little bit about propositions last time. These are sentences that are potentially either true or false. And we're going to use capital letters P to Z to represent sentences. So anything that's not P to Z does not count as an atomic sentence in our system. The reason why we do that is because A through O are going to be property letters. Later on in the course, we're going to use the first half of the alphabet in capital letters for something else. So that's why we carve off P to Z as sentence letters. Okay? So sentences are the basic unit, the basic thing out of which everything else is going to be built up in propositional logic. Every sentence has a truth value, or can be assigned a truth value. And that's just either T or F. And because the system is the most simple type of logic that you can do, we'll assume that every atomic sentence has a truth value and that there are only two. It's either true or false. There's no indeterminate, there's no in between, there's no, that was too vague to answer. It's either true or false. Just a note, please don't use 1 or 0 for this. So there'll be some parts of this course where you have to write down T or F, specifically truth tables. And comp sci people will be used to using 1s and 0s. Don't do that. Well, you can do it if you want, but we'll mark it wrong. Okay? So feel free to do this incorrectly, but the correct way is to write T or F. Okay? We're in philosophy now. This is truth and falsity. Come on, these are big ideas. All right. Okay. So atomic sentences, that's fairly straightforward. P, Q, R, these represent propositions. Now, we can build up molecular sentences from atomic sentences. And we're going to build them up using what are called connectives. So these are logical connectives. These are things that we use to make more complex sentences out of atomic sentences. And we have a few of these to learn. So today, I'm going to introduce you to 2 of them, negation and conditional. Before the first test, we're also going to learn conjunction, which is and, disjunction, which is or, biconditional, which is if and only if. Okay, so the reason why I'm just doing conditional and negation today is first, is to introduce you to the ideas of symbolization and derivation in the simplest ways possible. Right, so we're going to do a really restricted version of symbolization and a really restricted version of derivation so that those skills can be acquired fairly straightforwardly and then we can add complexity on later. That's the reason why we're doing just negation and conditional before we do the other connectives. Okay, so start with a simple negation. Negation is this little squiggle, the little tilde. It's also sometimes written as a line with a little down tick, but again, this is the symbol that we want you to write. there are a whole bunch of different ways of writing these same basic ideas, and I'm going to insist that you use the ways that I'm presenting in this course to write these down. So if you give us a different way of writing these logical symbols, we're just going to mark them wrong. And the reason I'm doing that is because I've been a TA for this course, and I know what it's like to be on your 400th logic exam. Your eyes are kind of going cross-eyed, your head is swimming, and some kid throws at you an unfamiliar formalism, and it's just extra, like it's a kind of marathon to mark these things. And I want all of the mental energy of our TAs to be dedicated to making sure they mark your test right, not to interpreting what it is you mean by your symbols. So that's the reason why I'm going to be strict about this, but that's the only acceptable sign for negation in this class. Okay? Just like with the T and false, I'm just imposing regularity on you so that the TAs get something that's very consistent so that they can spend their mental energy getting your tests marked correctly. Okay. So the negation sign is the most intuitive one. That's why we start with it. It's just whatever the truth value. Recall that we've got atomic sentences. P. P has got a truth value. It's either true or false. Now, we can build up a molecular sentence by introducing the connective. We say negation sign P, not P. Now, the truth value of that molecular sentence, not P, is just the opposite of whatever the truth value of P is. So if P is true, not P is false. If P is false, not P is true. It's really intuitive, hopefully. Yeah?
So there is no room for unrelated.
There is no room for unrelated. Yeah, that's important, right? So there's no, if you say, so we do this in normal language, we do this all the time. If you say, are you happy? And I say, well, I'm not unhappy. That's not really the same as coming out and saying, I'm happy, right? But in logic, it's exactly the same. In logic, something is either true or false. There's nothing irrelevant. There's nothing unrelated. There's nothing ambiguous, at least in this logical system that we're doing. So if something is true, the negation of it is false. If something is false, the negation of it is true. Okay. So, I am wearing shoes is true. I am not wearing shoes is false. This should be easy, yeah? Okay. Okay. The harder one is the conditional. The conditional is less intuitive. So the symbol for the conditional that we're going to use is this little arrow. It's also sometimes written as the sideways horseshoe. And again, I'm just going to impose that we're just going to mark this wrong if you write it that way. So use the little arrow. I know, there's nothing in principle better about the little arrow than the horseshoe. It's just that we need you to all be doing the same thing. Okay, so the conditional is very similar. It's intuitively closest to a sentence that says something like, if P, then Q. It's an if-then statement, basically. I say basically because it doesn't match exactly what we mean by those natural language sentences in some ways that I'll get into, but that's roughly it. The actual definition of these connectives is given in terms of what's called truth tables. This is the truth table for the negation. So we've got P, and we list all the possible truth values for P. All the possible truth values for P are given there, true or false. A connective is a kind of function, right? It takes an input and gives you an output, right? So negation takes one input, just whatever you're negating, and outputs something on the right. So the input is on the left, output is on the right. So if you input P, which has a truth value of T, the negation sign gives you an output of F, false, and vice versa, okay? So these truth tables are kind of the real definition of these connectives. They're how the connective acts truth functionally. Okay. That one was hopefully very straightforward. Here is the slightly more complex one for conditional. So the two left-hand columns there are both the inputs. So those are all of the two left-hand columns are all of the possible inputs for the truth values of P and Q. They can both be true, one or the other can be false, or they can both be false. Right? We see how that's all of the possible assignments of truth values to those atomic sentences. Okay, now these are truth functions, which means that if P is true and Q is true, then the whole sentence, if P then Q, comes out as true, right? So, if it is sunny, then I am happy. And then suppose that it is in fact sunny, and I am in fact happy, then that whole sentence, that conditional, comes out as true. Now, if it is sunny, and it turns out that I'm not happy, then the conditional, the whole sentence, if I'm sunny, then it's happy, is false, right? So those two first lines should be fairly intuitive. They map fairly well onto what we mean in normal speech by if-then. The weird bit are the second two lines. Anytime the first part is false, then the whole thing comes out as true no matter what. No matter what. This is slightly odd. And you know, if in natural language what we'd like to say is if the first part is false, then the whole conditional is just irrelevant. But we don't have that option in logic. Everything is either true or false, so we have to assign it some truth value. So we're going to assign it automatically true. So you can get some really weird things to be true given those two bottom lines. So anytime the first part of the if-then statement is true, the whole thing comes out as true, which is very counterintuitive. So suppose I give you the conditional if sharks drive cars, then I am president. That's true. Okay? If sharks drive cars, then I'm a mammal. Also true. Now that shouldn't make any sense to you. If that makes sense to you, something has gone terribly wrong. Okay? It just doesn't make any sense. It's just a weird fact about how the conditional works in our logical system, and it's a fact that's imposed on us by the fact that we don't have a space for irrelevant. Yeah? There's no truth value assignment that says, look, that just doesn't apply. Right? Doesn't apply isn't a word that we have in our logical system. We have to either given if P then Q, we have to be able to assign it some truth value or other. So we assign it true. So you feel free to try to make sense of this in your head if you want, but it doesn't really make sense. Okay? Okay. So, given that, what we've got is the following. We've got two ways, you could call them construction rules, for starting from an atomic sentence or a couple of atomic sentences and building up molecular sentences. So you can take an atomic sentence and negate it, or you can take two atomic sentences and join them with a conditional. Okay, so that's how you get the minimum level of complexity. And then what you get out of that, you can apply those construction rules again. So if you've got a conditional, that's a sentence in our system. It's a molecular sentence. It's a sentence in our system. And you can apply these rules to it again. So you can say, negate the whole conditional. Or you can make one conditional the beginning of another conditional. Right? So if P then Q, then if Q then R. You can build up more complex sentences using, so far we've only got these two construction rules. The textbook uses square and circle as kind of variables. I'm going to go back and forth, if you don't mind. I'm going to go back and forth. So when I stated these two construction rules, I used P's and Q's. I mean, I hope that it was intuitively obvious to you that you could have used this on X and Y just as well as P and Q, right? Like you didn't think this rule just applied to the letter P? Yeah? Okay. To avoid that confusion, in the Parsons text they use square and circle, which is also useful when the sentences become more complex. The square and circle version becomes more useful. So I'm going to kind of go back and forth between these two. So what's in that square could be a really complex sentence. It could be, you know, if P then not R, right? And then you say if P then not R, you can make a more complex sentence by just negating that. So the stuff in the box could be itself a complex sentence, which is one of the reasons the Parsons text uses this notation. So just a note, this is how the textbook talks about these construction rules, and I'll sometimes do this, and I'll sometimes do P and Q. Is that okay? Okay. I don't think, I didn't get anybody confused about this, so hopefully that should be fine. The molecular sentence, the complex sentence that you've built up out of your atomic sentences, gets its truth value in a truth functional manner. That is, the truth values of the parts are inputs to the connectives, which are like functions which spit out truth values. If what I just said sounds abstract, let me show you what this actually looks like. Okay, so this is just, so I'll show you in 1 minute. This is just to recall that simple sentence, so like not P is a molecular sentence. It's not just an atomic sentence. P is the atomic, not P is a molecular sentence. But then you can build up even more complex sentences using these construction rules. That's good, yeah? Okay. On Logic 2010, there's a module called parsing. And I did not assign you any problems from this, but it's nonetheless a skill that you really want to get good at. So I'll have some recommended problems for you that it's a good thing to learn. But parsing is the ability to see how a complex sentence is supposed to be broken down into its parts. And if you write your sentence properly, it will be completely unambiguous how it breaks down into its parts. The rules of how we write sentences are such that if you've done it properly, it'll always be clear how it breaks down. So for example, we very often use brackets to disambiguate. So not bracket, if not P then Q, is a very different sentence. It says something very different than not P then Q. Right? So the use of brackets is what helps clarify how the sentence gets broken down into its parts, and that matters quite a lot for like everything that we're going to do for the rest of the course. So your ability to symbolize, your ability to do derivations, your ability to do truth tables, everything I'm going to test you on depends on your ability to properly parse these sentences. So this is a really fundamental skill. It's one that I'm not really going to force you to practice because practically everything I am going to force you to practice presupposes that you can do this. So you'll get loads of practice on parsing. It's going to be implicit in everything that we do from now on. But let's talk about it specifically right now so that you're able to do the stuff that comes next. So parsing is all about figuring out which symbol is the main connective. The main connective determines the truth value of the whole sentence. So the parts of the sentence can have truth values. The whole sentence also gets a truth value. And that's what we're interested in. We want to know the truth value of the whole sentence, and that's determined by the main connective. Okay, and the main connective is the one that must have been added last as you're building up the sentence, right? It's the last connective that must have been added. You're thinking, how do I know which one was last added? I didn't see the sentence being constructed, Corey. You're being ridiculous. Hang on. So let's do some examples. This should become intuitively obvious to you. So it's not the case that if P then Q. Now, the main connective of this sentence is the negation sign. Because in order to get to this sentence by those construction rules that we just talked about, that has to have been the last one we added. Right? So we say this thing. So in the textbook, there's a bunch of examples of parsing stuff. here's how they do it. So this line coming down says the parts of this sentence are the negation and then this thing. And then this thing, if P then Q, itself gets broken down into parts. So we constructed this large sentence by adding P and Q together into a conditional. And then we made the whole sentence by adding a negation to that conditional. Okay? Now, we can feed truth values into this thing. So suppose green is true and red is false. How did I know that those are the truth values? I just made those up. Just for the sake of example, I just made up some truth values that we're going to feed into this and show how those truth values make the whole sentence true or false. Okay. So, if P is true and Q is false, what's the truth value of if P then Q? False. I heard false murmured over the thing. So recall that that's the one case in which the conditional comes out as false. So if I say, if it's sunny, then I'm happy, and I'm happy, and it is sunny, but I'm not happy, then that conditional was a false conditional. So if the antecedent is true, the first part is true, the second part is false, then the conditional comes out as false. So that I marked the arrow as the truth value of the whole sentence. Yeah? Okay. And then, of course, if the conditional is false, and then we've got a negated sign in front of the conditional, then the negation just flips it, right? The negation flips the truth value of whatever you fed into the conditional, the truth value of that gets flipped, so the whole sentence comes out as true. Okay? It could have come out some other way if I'd plugged in different truth values, but given those two truth values, this sentence comes out as true. Fairly clear how that works. So we've got truth values for the parts. The atomic sentences are the smallest parts of the sentence. And then the truth values for larger and larger parts get determined by how the connectives act. So the conditional has a truth table, and the truth table tells you, given these inputs, the overall truth value is this, and then that gets fed into the next level, and the next level, and the next level, until you have the truth value for the overall sentence. Okay. Slightly more complex one. So what's the main connective of this sentence? It's the middle arrow, right? The very middle one. Okay. So this sentence gets broken down into two main parts, if P then Q, and if not R then S. Each of those can be broken down exactly the same way into two parts themselves. P and Q, and if not R, then S. And we can do one last breakdown because not R is itself molecular into R. Okay? Okay. Now let's randomly assign some truth values to this and follow them back up through the connectives to determine the overall truth value of the sentence. So once again, I'm not getting these truth values from everywhere. I'm just making them up. Just making them up off the top of my head. Okay, so suppose that P is true and Q is false. P is false, Q is false, R is true, and S is true. Okay, so if you recall the truth table for the conditional, anytime, this is the weird thing about the conditional, anytime the first part is false, the whole thing is true. So that left-hand side, if P then Q, is going to come out as true. We've got a little bit of work to do to figure out what not R is going to say. So not R is going to be false, because it just flips whatever it is. Okay? Okay? And then once again, because the first part is false, that whole conditional is going to come out as true as well. Right? So those conditionals both get to be true. Okay? And then we're in a position to determine the overall truth value of that big molecular sentence that we started with. If the first part is true and the second part is true, then the conditional is true. Good. Good. Okay, so this is parsing. This is learning how to identify the parts within the parts of the sentence. And if you don't get this right, you won't understand what the sentence is saying. So not only will you not understand what the sentence is saying, when we get to derivations, you won't understand what you're allowed to do with it. So one of the most common errors that people make trying to do derivations is to misparse the sentence. So which rules you're allowed to apply to the sentence depends on what the major connective is. So we've identified the major connective, so now we know what we can do with this sentence in derivations. I'll show you that on Wednesday. But just the point is just you need to be able to parse these sentences properly in order to do everything else in the rest of the course. And everything else we're going to do in the rest of the course is going to be practice doing this stuff. So we will get very comfortable with this, hopefully. 2 construction rules, which makes this easy. So we're going to talk about the difference between official notation, informal notation, and not being well formed. So we got a very strict set of rules about how a sentence could look to qualify as official notation. We've got a slightly less strict set of rules for informal notation, and then anything that fails to be at least informal is not well formed. It's just nonsense. So you can tell that something is in official notation if you could build it up by following exactly these rules, these 2 construction rules that I showed you before. So if square is a symbolic sentence, then so is negation sign square, not square. And if square and circle are symbolic sentences, then so is bracket, square, then circle, close bracket. Those brackets are important. We can sometimes leave them off in some restricted circumstances, but generally speaking, you're going to need those brackets. So in informal notation, so for our purposes, the only difference between formal and informal is it's in informal notation if you could make it formal just by putting brackets around the whole sentence. So like, nobody's going to get confused about that thing that says if P then Q, right? The first line there, P then Q, there's nothing ambiguous about it. There's nothing confusing about it. So you don't really need to have those outside brackets. So if you leave those off, that's fine. Okay? That's the only, so far. As we add connectives, this is going to get more complex, the difference between official, informal, and not well formed. But so far, that's it. It's fairly straightforward. Okay. And the sentence is not well formed if it's not in official notation or informal notation. Now, these things sometimes look like sentences, but aren't. So, for example, here's a thing. So, sorry, let's take this out of here. Okay, so here's a thing that looks like a sentence. If P, then Q, then R. Right? That looks like a sentence. Because you can't have built that up following the rules. And it's not in formal notation because you can't turn it into something that's well-formed or in official notation just by putting brackets around the whole thing. What's missing in here is some brackets. We're missing brackets to disambiguate 2 different ways of parsing that sentence. So what I've shown you here are 2 different ways of parsing that sentence. So if P, then Q, then R could mean if P, then Q as one element, then R. So, and then that breaks down as on the left. Or it could say if P, then if Q, then R. And that breaks down as on the right. Now that's not well formed because there are circumstances in which the same way of assigning truth values to the parts gives you different truth values for the overall sentence. That's why this isn't well formed. One of the things that we want to have is that there's always a unique way of mapping from truth values for the parts to truth values to the whole thing. There should always be just one overall truth value for a given assignment of truth values of the parts. And that fails to be the case here. So here's the explanation. If what we meant by that sentence was if P then Q, right? P is false, Q is true, that means that if P then Q comes out as true, right? Because if the first part is false, then the whole thing comes out as true. And then we've got the overall sentence starts with something true and ends up on something false. And recall we said that's the only conditions under which a conditional comes out as false. So the first part is true, the second part is false. That means that thing on the left comes out as false on this way of assigning truth values to the parts. On the other hand, if what we meant was the thing on the right, P is false. Well, anytime you have a false first part, the whole thing comes out as true, right? So the same assignment of truth values gives us two different truth values to the parts, gives us two different truth values for the overall thing. And that's bad. That's exactly what we don't want to happen. We want the opposite of that to happen. We want it to be a unique mapping of truth values for the atomics to truth values for the overall molecular sentence. So that's why this is not well formed. What we need are brackets. We need brackets to tell us what are the parts of this sentence, you know? When we break this down into its parts, what are those parts? And that's what these two different ways of mapping it are, two different ways of breaking it down into its parts. Is that fairly clear why that's a problem? Yeah? So a list of, and it would have been a problem even if, suppose Q wasn't just Q, suppose it was some big complex sentence. All P, Q, and R each could have been molecular sentences in there. So long as there's something conditional, something conditional, something conditional, something conditional, something, yeah, then it's not well formed. You need brackets to tell you which is in the first part and which is in the second part. Okay. Here's one that's just nothing, right? People sometimes write stuff like this on tests. Like, you can't use the tilde, the negation sign is not a thing that you can put between two atomic sentences. You're never allowed to have two atomic sentences right beside each other. They need to be connected somehow, right? So this is nothing. This is nothing at all. Yeah? There's no valid way of parsing that such that you can figure out what would be the overall truth value given assignments of truth values to the parts. Okay, so I want to recommend that you try this. Try parsing. Do 1 through 10 this week. You're not going to get any points for it, but if you're at all uncertain about your ability to do this, and maybe you should be, unless you've done logic before, you should probably do this. So let me really quickly show you parsing on Logic 2010, and then I'll give you a break, and we'll come back and do more of this stuff. So really quickly, let me show you the controls for parsing. So close that. We're going to go into parsing. Okay, and we're going to select our problem. Let's select this one. Okay. So what it wants you to do is tell you whether it's either an official, informal, or not well formed. I think this is an official notation. It's got all the right bits to be an official notation. And then what you're going to do is just click on the thing that you think is the main connective. So what's the main connective here? This thing. This thing is the main connective. Okay? And then it'll pop up parts. If I'd done it wrong, let me show you what happens when you do it wrong. So what if I thought this was the main connective? nothing happens. Okay, so you click on the thing you think is the main connective. If you get it right, then the parts pop up. And then for those parts, you just do the same thing. So I think of this part, what's the main connective? Well, there's only one connective, so that's it. Of this thing, what's the main connective? It's this thing. Okay, so now I've broken that complex sentence down right into its parts. I think it's an official notation. I say check, and it tells me I'm correct. Okay? So that's parsing. Nah, I don't want to save that. So again, recommend that you try that. I'm not going to require you because you're going to have parsing practice throughout the semester on practically everything else that we do. But there's that in case you want it. So that was the first half. We did just kind of the really basics of what is an atomic sentence, what is a molecular sentence. We did parsing. Now we're going to move on to symbolization. So this is going to be one of the main skills of the class. We're going to do symbolization from here on out for the rest of the semester. Symbolization is one of the only points at which this stuff interacts with natural language. We call it natural language, the stuff that's coming out of my mouth right now, as opposed to formal languages or artificial languages, which are like logical symbolism. So symbolization is how we get sentences from natural language into our logical system. So, and we'll just talk about how to symbolize the conditional and the negation. So, symbolizing negation is exactly as intuitive as you might hope it would be. If I have P is it is raining, then not P is it is not raining. Something like that. Or it is not the case that it is raining. It's also not P. Or it failed to rain. Yeah? Like, that should all be incredibly obvious and intuitive. These are just what we call stylistic variants. So it is not raining, it's not the case that it's raining, or it failed to rain. Different ways of saying something that is logically equivalent. It's all equivalent to not P. Yeah? Okay. There's one small wrinkle with the negation, and it's the question of what the negation applies to. And the rule is going to be the following. Not and fail to give a negation that applies to the smallest sentence that they are part of. So suppose the sentence to be symbolized is, if Roberta doesn't call, Susan will be distraught. So the negation, if you're turning that and P is Roberta calls and Q is Susan will be distraught. If you're turning that into a logical sentence, what you want is to apply the negation to the smallest sentence that it's part of. So Roberta doesn't call. Yeah? So the negation goes on not P, which is a very different sentence than it's not the case that if P then Q. Okay? So applying negations to the smallest parts, and that assumes that you know what the parts of the sentence are, how to break the sentence down into parts, which is something that we'll talk about extensively. So if it's not obvious to you what I mean right now by the smallest parts of the sentence, don't panic. That's going to be a major subject of our discussions of symbolization from here on in. So the task that I'm going to assign to you is I'm going to give you, so on the tests, on the exam, what I'm going to give you is a sentence, like, for example, if Roberta doesn't call, Susan will be distraught. And I'm going to give you a symbolization scheme. So something like P is Roberta calls and Q is Susan will be distraught. So that's what I'm going to give you. And then what your job is going to be is to write down the symbolic sentence, if not P, then Q. Okay? So that's going to be the task. It's very similar to the task that you'll be given on Logic 2010, where it gives you a sentence, and then it gives you a symbolization scheme, and then you have to work out how to pull that sentence apart into parts and assign logical symbols to those parts. Okay, so I hope negation is fairly straightforward. Negation is not that hard to get a handle on. It's just, you're just saying not whatever the thing is, right? Once again, conditionals are the hard part. So what does the conditional mean? And we're basically going to spend the rest of this class talking about what the conditional means and how to translate it into sentences. Basically, the conditional means that if P is true, Q has to be true also. If P is true, Q, so a conditional guarantees that given the truth of P, Q will also be true. Now, as we discussed earlier, if P is false, then the conditional is automatically true. And in any normal natural language scenario, what we'd say is the conditional is just irrelevant. Not that it's true, it's that it's irrelevant. But we don't have irrelevant as part of our system. We have only true or false to work with. So we have to say that it's automatically true. Okay. So that's roughly what the conditional means. It's a kind of guarantee. It guarantees that if P is true, then Q is going to be true also. Yeah, we've talked about this enough. So I'd also like you to know the parts of a conditional. There are two parts to the conditional. This sort of started slipping out my mouth a little bit. I've been calling them the first part and the second part. Here's the technical vocabulary for this, and you do need to know this. You do need to know these two parts. The antecedent or the antecedent, both ways of saying it are fine, and the consequent. The antecedent and the consequent. The first part, the if something something, and the second part, if it's raining, is the antecedent, then the sidewalk is wet, is the consequent. Okay? So you'll need to know those terms for the rest of the semester. Those are going to be relevant to practically everything that we do. The antecedent and the consequent. Okay? Now it's a little misleading to call that the first part and the second part, because the antecedent doesn't always come first in the sentence. So you could say the following. You could say the sidewalk is wet if it is raining. And that's the same as as if it's raining, then the sidewalk is wet, right? It's the same basic idea. I'm conveying the same facts would make that sentence true or false, right? So calling it the first part, this is why we don't call it the first part and the second part. We call it the antecedent and the consequent. Yeah? Right, so in symbolizing these things, that's right. So in writing these things out, the antecedent always comes first, right? So writing it out in logic, the antecedent always comes first, the consequent always comes second. That's their position in the logic of the thing. It's just that in natural language, we often flip those things around. Good. So suppose S symbolizes Maria sings, and X symbolizes Javier will leave. So these are all stylistic variants. These are all different ways of saying if S, then X. So if Maria sings, Javier will leave. Provided that Maria sings, Javier will leave. Assuming that Maria sings, Javier will leave. Given that Maria sings, Javier will leave. In case Maria sings, Javier will leave. On the condition that Maria sings, Javier will leave. So that's not an exhaustive list of the ways that we sometimes give conditional statements, but that's a good sample of all the different ways, a bunch of different ways in which, so all of those sentences, using the symbolization scheme I just described, all of those sentences would be symbolized as if S, then X. Yeah? Is the point here clear? There's a whole, so I'm going to give you on the test and exam, I'm going to give you a sentence of one of these forms, and it's going to be up to you to identify that one part is the antecedent, one part is the consequent. Okay, and just to reiterate what I just said, it's very often the case that we don't put the antecedent first in the natural language sentence, right? So I hope that it's clear to you that all of these are exactly equivalent. All of these are also symbolized as if S, then X. Javier will leave if Maria sings. Javier will leave given that Maria sings, and so on. Yeah? So just because one thing comes first in the natural language sentence doesn't make it the antecedent. Okay. Here's just another way of saying what the conditional says. All of the cases where S are true are cases where X are true. Right? So the set of S cases is entirely contained within the set of X cases. It's another way of putting it. Yeah? Now, that's compatible with the S cases and the X cases entirely overlapping. There's nothing in the conditional that says there are X cases that are not S cases. Right? It's okay that if they're overlapping. And in fact, this is going to be the case with what's called the biconditional. If we say if and only if, then that's the situation. There's a perfect overlap between both types of cases. The only thing that's ruled out by the conditional is the following: some S cases that are not also X cases. Right? So there's some, you see there's some overlap, there's some S cases hanging out there that don't fall under the X cases. This is what's ruled out by the conditional if S then X. Right? Okay, this is just, again, by way of going through the conditional. Hopefully this is just, I'm going to give you a bunch of ways of thinking about this conditional that hopefully make it more intuitively clear to you. Okay. Now, only if is a complication that you'll need to get a handle on. So only if kind of reverses things. So if Maria sings, Javier will leave gets symbolized as if S then X. We're okay with that, right? What if I said only if Maria sings, Javier will leave? That now gets symbolized as if X then S. Flips it around. Only if flips things around. Okay. Oh, I've gone off the edge of my apologies. I've gone off the end of the world. Okay. So I'll try to make this intuitive for you. We might end up, if this doesn't work for you, I'm going to spend a little bit of time trying to make this intuitive. If it doesn't end up being intuitive, then I'll show you just the rule that you can apply mechanically in a minute. So try to get this, but if your mind just slips off of this and it's not working, I'll give you a rule very shortly. So what would make these two sentences false? That's probably the easiest way. So how do you falsify these two sentences? What would make them untrue? So what would make the sentence, if Maria sings, Javier will leave, untrue? What sort of scenario would show you that that conditional is false? Yeah. Exactly. Maria sings, but Javier sticks around, right? So that's the second line on the second truth table. S is Maria sings, Javier does not leave. He fails to leave. So it's false that Javier leaves, right? So that's what would make that sentence false. How about the second case? Only if Maria sings, Javier will leave. What would make that false? Yeah. Right. Maria fails to sing, but Javier does leave. So saying only in the case that Maria sings will Javier leave. In any other case, he's sticking around. That's made false if she doesn't sing, but he leaves anyway. Yeah? So if X then Y gets flipped around by only if. Only if says, here are the only conditions under which this thing will happen. And that flips the conditional. Okay. But that's kind of, to be honest, thinking about it in terms of flipping the conditional can be confusing because of that thing that we just talked about where You can have the conditional in either order, right? So sometimes you have to do a double flip in your head, and it's really like too much for me. Too much for me personally. So here's how I think of it. Here's the mechanical rule. In case that didn't really make sense to you, here's the mechanical rule that you can use. Whatever comes directly after if is the antecedent. Whatever comes directly after only if is the consequent. Okay? So let's look at these earlier examples. So, okay, here's an example. If there is fire, then there is oxygen. Right? True, right? Anytime there's a fire, there must be oxygen present. The presence of fire is a guarantee of the presence of oxygen. All of the fire cases are contained within the oxygen cases. It's just saying this a bunch of different ways. That's equivalent to saying only if there is oxygen is there fire, right? Those two sentences say the same thing, right? They're both claiming that all of the fire cases are contained within the oxygen cases. Yeah? Now, in the first sentence, the thing that comes right after if is the antecedent. P, there's fire. Right? The antecedent is the first part. Once you got it into a logical form, in the logically symbolized, the antecedent is the first part. If P, then Q. The thing that comes right after only, in the second sentence, the thing that comes right after only if is the consequent. Yeah? Only if there is oxygen, there is fire. Okay, so now I'm going to flip the order of the natural language sentences around, and it'll be the same. There is oxygen if there is fire. Saying the same thing. All these sentences say the same thing. If P, then Q. There is oxygen if there is fire. But now the if comes in the middle of the sentence rather than the beginning. Right, so the antecedent comes at the second half of the sentence, but it still comes right after if. Whatever comes right after if is the antecedent, even if is halfway through the sentence. You figure out that that's the antecedent, and then whatever left over is the consequent. And there is fire only if there is oxygen. Whatever comes right after only if is the consequent, even if only if comes halfway through the sentence. Yeah? Ah, yes. It is. Good. Okay, so here's another way of cutting through this, necessary and sufficient conditions. So the sentence, if P then Q, says the following two things. Q is necessary for P, and P is sufficient for Q. Okay? So here's an example to think through this. If you're a dog, then you're an animal. True, right? There's no dogs that aren't animals. All of the dog cases, anything you find in the world that is a dog, is contained within the set of things that are animals, right? Excluding weird robotic dogs. Let's just assume that we're not talking about that. So that's the same as saying being an animal is necessary for being a dog. You can't be a dog if you're not an animal. It's necessary. Now, it's not necessary to be a dog to be an animal, right? Not all animals are dogs, right? But it is sufficient. So being a dog is sufficient for being an animal. Yeah? So this is necessary and sufficient conditions. So if I give you the sentence, being an animal is necessary for being a dog, and P is an animal, P is being an animal, and Q is being a dog, what do you say? Sorry, P is being a dog and Q is being an animal in this case, to make it match my slide from before. Being an animal is necessary for being a dog. Being a dog is sufficient for being an animal. Right? And it's about this containedness stuff. It's about the fact that all of the dog cases are contained within the animal cases, but not the other way around. How's that? Okay. So that's enough on basically what the conditionals are, what they mean. I'd like to point out that some sentences are ambiguous. This is the elephant of ambiguity that we will hunt down and shoot. Here's an ambiguous sentence. It's not the case that the dog will bark if the mailman comes. It's not the case that the dog will bark if the mailman comes. Now, you could mean two different things by that. You could mean two different things, and they have different logical structures. So D is the dog will bark, M is the mailman comes. I apologize, I've violated my own rule about only using P to Z, but I think it's more intuitively clear. So that sentence could mean, if the mailman comes, then the dog won't bark. Right? That's a guarantee. So what you're saying there is the mailman coming is a guarantee of the dog not barking. Yeah? There's one thing you could mean by that sentence. Here's another thing that you might mean by that sentence. It's not the case, not, bracket, if the mailman comes, then the dog will bark. All that sentence says, that second sentence is not a guarantee that if the mailman comes, the dog won't bark. What you're saying is, I'm not guaranteeing. It's not the case that I can guarantee that all of the dog barking cases are contained within the mailman coming cases. Sorry, the opposite. All of the mailman coming cases are contained within the dog barking cases. So that sentence is ambiguous. That sentence could be legitimately, logically symbolized in at least two different ways. Now, I'm going to try my very best to not give you sentences that are ambiguous without telling you that they're ambiguous on the test. So, sentences, so when you're doing symbolizations, I'm going to do my very best to give you unambiguous sentences most of the time. And then once in a while, I will say, this sentence is ambiguous. Tell me the way in which it's ambiguous. Tell me two different ways you could symbolize it. It's never going to be the case that it's ambiguous and I want you to figure out one way rather than the other. And if by accident I give you an ambiguous sentence and some people symbolize it one way and some people symbolize it another, both groups will get the marks. That's how we'll deal with that fairly unfortunate circumstance if it arises. Gonna try our best not to do that to you. Gonna try our very best not to give you ambiguous sentences without telling you they're ambiguous. If I do by accident do that, then either reading will be fine. Either reading will be worth the marks, okay? Let me just show you briefly that this matters. So here's a way in which assignments of truth values to the parts of that sentence end up with different truth values to the overall sentence. So if both M and D are false, the overall truth value of that sentence comes out opposite, given those two ways of reading it. So these ambiguities can make important logical differences. It's not just that it's the same sentence written two different ways. It's two logically different sentences, two sentences that are not logically equivalent. And when I say they're not logically equivalent, what I mean is, given one assignment of truth values to the parts, you get different assignments of truth values to the overall thing. So that's ambiguity, and it's one of the reasons that we're learning this stuff. So one of the problems with natural language is that we say ambiguous stuff all of the time. And usually it's the sort of context and it's knowing the person that lets you disambiguate or asking follow-up questions. But suppose you want to get all of the ambiguity out of the things that you're saying, knowing logic is one of the ways you can do it. And knowing logic, actually one of the things that it will do for you is to help you identify the ambiguities in things that you're saying and things that are being said to you. So you can see how something is ambiguous, identify that, and then ask the relevant follow-up question. Do you mean that you're sure that the dog won't bark if the mailman comes, or do you mean that you're not sure that if the mailman comes, the dog will bark? Tell me which of those two things you mean. So one of the reasons why we're doing this is to identify ambiguities like this and to sort of help us eliminate them. Okay. So when we're symbolizing, doing these symbolization questions, commas are really important information. I know that most of the time if you're a good reader, you probably don't even see the commas, right? You just absorb them passively. But in this class, you're going to have to really focus on commas. Commas are incredibly important information for you because they help to tell you what the parts of the sentence are. Commas carve sentences up into their parts, and I disambiguate the meaning of the sentence by placing a comma here rather than there. So it's not the case that, comma, the dog will bark if the mailman comes. So now we're saying, I'm saying it's false that this whole thing, right? And that's not if M then D. Compare that to, it's not the case that the dog will bark, comma, if the mailman comes. Now, the thing after the if is the antecedent, and the whole rest of the sentence is the consequent. Right? So by placing the comma in one part of the sentence rather than the other, I've given you information about how the sentence breaks down into parts, and how the sentence breaks down into parts radically informs, importantly informs the structure of the sentence, the logical structure of the sentence. So you should keep this in mind. This is an important thing for your life. Keep in mind, you can do this with commas. Your commas are how you tell your reader how to read the sentence, that is, what the parts of your sentence are. So when you're doing these symbolization questions, those commas are going to be very important information for you. They're going to be your guide to how to put the sentence apart, pull the sentence apart into its parts. Yeah? Okay. Okay, so briefly, I just want to show you symbolization in Logic 2010. So I told you that I would do this. I told you that I would give you some guidance on how to deal with this program. So I showed you parsing already, so we're going to go to symbolization this time. Okay. Now, as with in every module, you select your problem. So we'll do the question 1 right now. Okay, so I want to point out a couple of things that are going on the screen right now. I would like to make this screen smaller so that you can see it. Okay. So, two things on the screen right now. On the left, you have what's called the symbolization scheme. That tells you which letters stand in for which propositions. Okay? So here we've only got one proposition to work with, W. W means the Bruins win. The sentence to symbolize is the Bruins fail to win. Okay, it's not that hard. What's the answer to this? Not W. Not W is going to be the answer. Okay, so how do I type that in? there's at least two ways you could input that answer. So the kind of slow and careful way is I'm going to right-click on this sentence and tell it what the main connective is. So I'm going to select from this list what the main connective is. The main connective of not W is not. That's the negation. So now it gives me negation something. Now, if you want to, if you feel like it, you can type in what you think the rest of the sentence is. So the Bruins win. Okay, so not the Bruins win. This is just a way, it gives you the choice to do this if you want, because sometimes when we get deeper into this, the sentences are going to be big and long and complicated. So you might want to type these in just to keep it clear in your head. But notice that this is not yet complete. Okay? So to complete this, you don't need this at all. I don't need to have typed this in. What I need to do is right-click on here and say atomic and type in the atomic, the relevant atomic. And it's got to be uppercase W. Lowercase w won't do the trick. Uppercase W. So now I've got not W. And now I've got the right answer. Okay? Okay, there's one other way. Okay, so on Macs, you don't have a right click. You have a control click. Control click will bring that drop-down menu for you. There's one other way to enter your answer. You can click on direct. So direct brings this thing up, and I can just say not W, type out the answer, and that gives me this. And that's also true. Okay? And once again, to remind you, you must click submit. You type out your password. You say OK. Yes, I want to save the current problem. And then you submit. You can submit one question at a time. You can submit a block of questions by holding Shift and saying submit. Yeah? OK, let's do one more, yeah? So, okay, so this time we've got two atomics to work with. We've got W is the Bruins win, and R is Bruins go to the Rose Bowl. Yeah? Okay, so given that, is a stylistic variant for what? If. Right? So this thing is a conditional. So we're going to right-click on here. We're going to say conditional. And then we have to fill out the two parts of the conditional. If this was a really complex sentence, it might have been another conditional and then another conditional. Like you can get pretty complex. You will get complex but by the end of the semester. Suppose I want to clear all that. I say delete. But so conditional. Feel free to type in the sentences if you want, if it helps you to keep this in mind, but that's not what you have to do. All I have to do is say on this one, atomic, capital W, OK, and then right-click on this, atomic, capital R, OK, check, correct. Save, submit, and you're done. OK? So that's symbolization on Logic 2010. Hopefully that's fairly clear. That's it for this time. Next time we'll do derivations.